All right, one more effect on the equilibrium, right? We have seen in the past that when you apply stresses onto the equilibrium, so the equilibrium will adjust itself to stay on equilibrium, to relieve the stress and regain the equilibrium. We have seen that we can do pressure, volume, concentration, right? But this concentration, pressure, volume do not change the value of Kc, right? So, for example, the ammonia synthesis, we have seen this many times now, right? The Kc of this synthesis is still 0.291. No matter what you change pressure, volume, concentration, still 0.291. But if you change the temperature, the Kc change. Take a look right here, right? At low temperature, 300 Kelvin, so 300 Kelvin, the Kc is really high of this equilibrium, really high, 10 to the F. Really favor ammonia. But at high temperature, as high as 1,000 Kelvin, Kc is really low, so 10 to negative third, 10 to negative third, 10 to negative third right there. You know? That's why this equilibrium is not suitable to make ammonia at high temperature, because this at high temperature, this equilibrium favors the product. Also, favors the reactant. But at low temperature, when it favors the product, at low temperature, reaction really slow. I mean, it's not suitable to make ammonia. Right? Now, how to explain the changing in temperature affect the Kc? Here's how I explain it. Right? So, if the reaction that you're dealing with or equilibrium is exothermic reaction, take a look at the ammonia synthesis. So, ammonia synthesis is an exothermic reaction. Exothermic means release heat, right? So I'm going to include the heat or the energy into this reaction. Since this reaction release heat, I can put reaction as the energy as a product. Does it make sense? Because it release heat, the reaction release heat, so heat's coming out, right? If we add heat, increase the temperature, add heat into this reaction, what's going to happen? Well, you're going to treat this heat, this energy right here, just like one of the products. If you have more product, what's going to happen to equilibrium? Shift backward. Here we go. All right. Now, if you remove heat by putting this reaction flask in the fridge, so it's cold. So basically, we're removing the heat. What's going to happen? Well, removing the heat, removing the product, the reaction shift forward. That's it. Really simple there. All you need to know is if the reaction that you're dealing with exothermic or endothermic. Okay. Now let's take a look at an endothermic example. So this equilibrium is endothermic, so absorb heat. So I can include the energy right here as a reactant. Right? And if you add heat into it, let's say you heat it up this reaction. Too much reactant now. What's going to happen to this equilibrium? Shift to the product. Yeah, right? Now go backward. So one more time. So if in this case, if we remove heat, put this in the fridge. So we remove the reactant out of the equilibrium. What's going to happen to the equilibrium? Shift backward to make more reactant. Right? That's the reason why this happened, right? If you remember, so N2O4 has no color, and NO2 has brown in color. At low temperature, so we remove heat, the equilibrium shift backward. That's why the color of this equilibrium is no color. So because this equilibrium shift to N2O4. But if you heat it up, so at 25 degrees, so at room temperature, right? So and when you have a lot of heat, so we add more heat into this reaction. Too much reactant, shift to the right, make more NO2. You see brown in color. See that? That's the whole point of the energy and equilibrium, right? Heat and equilibrium. So, all right, let's try this one. So if you get what I said, okay? If heating the equilibrium below, what color of solution would you expect to observe? Okay, and so we have pale pink as a reactant and deep blue for the product, right? Cobalt tetrachloride. That's the cobalt 2 tetrachloride. The enthalpy or the heat of reaction is more than 1. So plus sign, right? Is it endothermic or exothermic? Plus. Go back here. Plus endothermic. So this reaction absorb heat, right? So if this reaction is absorb heat endothermic, so we can include the energy on the reactant side, as a reactant, right? And the question asks, if heating this equilibrium, so we add more heat. In this case, you add, basically, it's like you add more reactant. What's going to happen? What does equilibrium going to do? Shift to the product. Good. Shift to the product. And what color you going to see? Go toward deep blue. Go toward deep blue. Here we go. Go toward deep blue. Okay. If you cooling this reaction down, the reaction going to shift backward to pale pink, and you're going to say pale pink. This is real. I'm not making it up. This is people do it. You know? All right. Okay, that's it. All right, let's go to last one. So we got catalyst. Okay.